Recording is rolling. It is Monday, November 18th. A bunch of you guys just turned in your energy quiz to the grade tray. I'll get those graded soon. Like the centripetal force, gravitation, orbits quiz, I went ahead and returned those. Some students never turn them in. I figure if it's not by now, probably never going to get back in. So those are back to you guys. If you guys want to do corrections, you can turn to corrections. That's right. Okay, so tomorrow there's an ASVAB assembly in the, wait, where was that? Auditorium, I think. Hold on, I forget. Anyway, there's an Excel file. That's it. It has a list of students' names. I went and cleaned it up, so it's just your name if you're attending. I think you guys back last week, I called out about 6 or 7 of you guys if you were on the list, if I saw your name on the list. Anyway, I uploaded that cleaned up Excel file to Google Classroom. So if you think you might have to be in that ASVAB assembly, go ahead. All right, you guys know there's an in-class quiz coming up. I'm gonna bump that to Wednesday. I think I'll do a 2-day review with you guys, 2 days. So today and tomorrow, plus that makes sense with the assembly coming up, right? And also, it looks like we're not going to get that hurricane on Wednesday. I mean, it'll just be a kind of dissipated storm. So I'm pretty sure we're going to have school on Wednesday. Let's do the in-class quiz then. The in-class quiz is going to be on projectiles, forces, Newton's law, and energy. So pretty much kind of everything we've done except for any kind of rotational or gravitation motion. Yep. 33. It's 33 questions. Yeah, 33 questions. Right, but I think you guys will be able to do that in class, so one class period. All right, if you guys are taking notes or put some notes together, you guys can bring in 1 8.5 by 11 page of notes, or just something. If it's line paper for your notebook, that's okay. It's about the same size. Okay. I think you'll be able to finish it. Yeah. Uh, well, then I'll figure out what then. I guess you're gonna. We'll see. We'll see. You might spontaneously combust. Oh, need a quiz. Let me see. You need this one. All right. Okay. All right. Let's see what's next here. Okay, guys, the next topic we're going to be talking about here, just a little sneak preview here is momentum. You guys see the new posters hanging up with the blue banners? You guys' thumbnail notes, the blue banner ones. Usually if you see a collision, I'm going to start this Thursday and Friday. Kickstart this, right? Usually if you see a collision, you have to use this momentum. It's just mass times velocity. It's a vector value. So direction matters if it's going backwards or forwards. It's conserved during collisions. You can solve stuff with that. So I did upload a bunch of files to Google Classroom if you want to go take preview ahead about kind of stuff coming up. I opened up the next AP Classroom, which isn't due for a couple of weeks, but there you go. All right, so you guys know what we're doing, where we're going. All right, guys, all good. All right, keep going then. So let's go way back. All right, wow. Good day. All right, vector components. You guys remember this right here? Okay, so there's a right triangle here, but then overlaid on top of that, have say this black arrow vector, which has a magnitude, like how long is it? It can measure so long, right? And also a direction. That's this angle theta. Okay, guys, write in your notes. Here, we're going to do a kind of an active review here. You guys got some notes out, right? Everybody got some paper? If you don't have paper, you got some on the stools. Right? Go ahead and write down A equals and write it in terms of C and theta. Guys, write A equals and then write B equals and write that in terms of C and theta. So write A equals and B equals. It's a real short equation, but I guess two equations, right? A equals, B equals. Can you guys see that? A equals, B equals. And then in terms of C and in terms of theta. You guys remember vector components? Right? Like how much over? How much up? You guys have probably seen hundreds of these by now, right? All right, everybody got it? All right, so here, guys, write A equals and B equals. You know, that refers to this A and this B, right? Can you write A and B in terms of C and theta? You guys have done hundreds of these, right? Yeah, guys. Have you never seen sine and cosine? Oh, yeah, thank you. Here, let's do a numerical example. Guys, suppose I'm pushing this up to the right. I'm pushing with 5 newtons of force at a 37-degree angle. Can you guys do that? Yeah, guys, how much am I going strictly to the right? That's right. 5 newtons times cosine of 37 degrees, which happens to be how much, by the way? 4 newtons. Okay. And what's this one right here? 5 newtons times sine of 37 degrees. Yeah, which is 3 newtons. You guys remember that, right? Right. Now, all I done is I just take the numbers out and just replace them with letter type variables. That's all. Same thing. Update this here. Eric is present, I think. Something like this. All right. Here's a little bonus question. Can you guys solve for this theta in terms of, let's say you know the sides. Let's say you know this is a 3, 4, 5 triangle. With, I don't know, maybe it is, or maybe not. Okay. Can you solve for this theta in terms of the sides? Given that it is a right triangle. So I'll give you it's a right triangle. Okay. Can you guys do that? All right. Boom, boom, boom. Is that what you guys just wrote? So B is equal to C sine theta. A is equal to C cosine theta. And here's usually the way I get tangent get that angle theta. You have to take an inverse trig. Now, if you do an inverse tan, it's the ratio of the two legs. Okay, remember that? Okay. Here, and while you guys are jotting that down, I mean, it's in your thumbnails anyway, but it's just review first. Here, I'll prove it to you guys. What's inverse tan of, if this is 3 and this is 4, this could be 3 over 4, right? 3 over 4. Okay. Guys, when I hit enter, what number did my calculator say? 37? Boom, there it is. 37 degrees. Oh, yeah. All right. It's got 37 degrees. All right. All right. Move on. Let's see what's next here. Okay. Yeah, you guys did a lab version of this. All right, you guys remember that? All right. I had you guys do some measurements, do some calculations, and they all align. Oh, yeah, that's right. The calculations and the measurements align. All right. I'm going to go ahead and recap all of the kinematic motion. Kinematic motion is in 2 halves. There's the linear motion half, and then there's the projectiles. So from 1 dimension to 2 dimensions, right? But you guys remember, we're dealing with like distances, times, velocities, and accelerations. You guys remember that, right? All right. Oh, one of the first big labs I had you guys do was this car and incline lab. You guys remember that? The car and incline? Okay, that's the next page. You guys remember this car? Zip it down like that. Okay. And we're looking at a bunch of relationships. So, well, here, I don't have a super good way to cover these up in limited time, but guys, any of these graphs, you should be able to draw from scratch. AP could ask you any of these graphs. So you should, oh yeah, right. So for example, guys, distance versus time. Guys, what's the equation of this curve right here? X equals 1/2 AT squared. You guys remember X equals 1/2 AT squared? Right? Right. So that would be a parabola, wouldn't it? Right. Now, if you wanted to linearize that, could you graph X versus T squared? And that would look like this one right here. Here's X versus T squared. Right? Hey guys, what's the slope of this line equal to? There's a classic AP question right there. Guys, what's the slope of this line equal to? 1/2 A. Yeah, 1/2 A. Right? Guys, isn't the equation of this line X equals 1/2 AT squared? So the slope is 1/2 A. That gives you X is 1/2 A T squared. Right? Just like that. Right? Is that true? Right. Here on the right side, I put your classic X versus T, V versus T, A versus T. That's kind of the organization of this page. You guys see that? X versus T, V versus T, A versus T. Right. Guys, how many times have you guys seen these 3 graphs? In fact, there's more posters coming up with exactly this you're going to see again. Right? Right. Parabola, linear, constant. Right. You guys see that? Right. Guys, suppose you change out the mass of the car. What if you have this car go down, beep, and you replace it with this guy? Now my turn. Guys, which one reaches the end first? Same time. So if you did mass versus time, you could get this graph, right? You have different masses. They're all the same time for the same distance. Guys, you do that? Okay. Now the little bit tricky ones. Do you guys remember an equation that goes v squared equals v naught squared plus 2ax? You guys remember that? Right. That's kind of these guys right here. So, guys, this is a square root right here, v versus x, right? So here, how about this? Okay, suppose you have a track, 2 tracks side by side. One's real short, maybe it's like 10 centimeters, whee, and the other one's like 90 centimeters, whee. It's like 9 times the distance. Guys, if you have 9 times the distance, how's the speed of the car going to compare at the end? 3 times? That's right, 3 times, because that's this graph right here, right? And that's the equation. V squared equals v naught squared plus 2ax, right? So if I have 3 times the distance, 9 times the distance, I'll have 3 times the speed because it's a square root. Okay, you guys remember that? All right, and then here's the linearized version of that. All right, so There's a classic. I've never stopped referencing this slab, and I'm going to keep referencing all the way up until you actually take the exam in May. All right. Car drives at constant velocity. I have three sets of axes set up right here: X versus T, V versus T, A versus T. Right, you guys know the three classic kinematic graph setups. Okay. And so what do those graphs look like? Can you whip them down real fast? If your hand is in motion with the pencil in your hand, then your brain is making more neural connections. It's going to help you out a bit. I'm trying to go through this kind of fast to do this review in 2 days, but if you can whip them off real fast, X for T, V versus T, A versus T. Guys, constant velocity. You're on I-95 cruise control, just going. How far have I driven as a function of time? How fast am I driving as a function of time? What's my acceleration as a function of time? Just cruise control, just straight up towards Jacksonville. Guys get that? All right, you guys got the graphs? Did you guys draw, boom, those three right there? All right, linear, constant, zero. Boom, boom, boom. All right. Is there any question why those graphs look like that? Okay, because here, if you drive for 1 hour, maybe you've gone 60 miles, drive another hour, go another 60 miles, drive another hour, another 60 miles. That's linear. Right? Your speedometer is just the same, 60 miles an hour, 60 miles an hour, 60 miles an hour. You're off the road, you're going slow. And you're not speeding up and not slowing down. Like, no, I'm going the same speed. So your acceleration is zero. You guys see distance equals speed times time? And then if you want to, you could rearrange it, get any of those, right? All right. See what I got next. Acceleration. So speaking of acceleration, we talked about two types of acceleration. Guys, what's a brief formula you can write for linear acceleration? How could you calculate linear acceleration? Aha, exactly. Change of velocity over change of time. That one right there. Right? In fact, for the first few weeks of this class, that's the only type of acceleration we talked about, right? It's just speeding up and slowing down. That's it. This is tangential acceleration, linear acceleration, but change in velocity over change in time. That's all that is. Right? You're watching your speedometer needle move. How fast is your speedometer needle moving? It's the rate change of velocity, right? Then it wasn't until more recently we got into this going around a curve. Does anybody remember going around a curve? Yeah, there you go. Exactly. V squared over R. Although that's not going to show up on the quiz on Wednesday, but you guys know that too, right? Right. We see that. Wait. All right. All right. All right, next one. Guys, I got 3 kinematic formulas. Guys, write them down real fast. Write down the 3 kinematic formulas. I think you guys probably have these memorized by now, right? Just because you've been applying them hundreds of times. I mean, literally hundreds of times you've applied these in this class. Right, so probably just by using them, you've memorized them by now. All right, you guys got the 3 kinematic formulas? 3 kinematic formulas. In fact, I reference them so much, I got them set right on my board right here with the magnet. Boom, right there. All right, you guys got the 3 kinematic formulas? Did you guys go x equals v naught t plus f a t squared? Right? And if you break it down, guys, if there's suppose there's zero acceleration, you're back to cruise control. Hey, look at that. It's good old distance equals speed times time, right? And then let's do the other one. Suppose you go to the edge of a cliff and you drop a ball. That's v naught is 0. Sorry for breath. Hey, look who it is. That's equals 1 half at squared. Which I think we talked about that one before, right? For the car rolling down the incline. Okay. So there's distance as a function of time. Maybe you have initial velocity. Maybe you have an acceleration. Maybe you have both. Put them all together. Okay. Guys, what's the second kinematic formula? Vf equals. Aha, boom, v naught plus at. How fast you're going is how fast you were going plus a times t. Right? And how's the third one go? Aha, all right, there you go. V squared equals v naught squared plus 2ax. Right, so depending on the variables you have. All right. All right, so you guys good with the kinematic? Right. Actually, I have 2 of these. Here's the one without all the units written. Because that's a point I always emphasize too. Is guys, in this class isn't just numbers. Like these are physical values with units attached. Guys, meters, this multiplies to meters, this multiplies to meters. Can I add meters to get meters? Yeah, in fact, that's the only thing that it works. Guys, can I add gallons to miles to get meters? No, that doesn't make sense, right? So you can only add or subtract like units, right? Okay, if you can identify any three, you can solve with those equations, right? Sometimes something's applied, like a gravity field or starting from rest, or something goes to a stop. They might not explicitly type the number. Okay, like that. All right, good. All right, we're about to go to a cliff, drop a ball. X versus T, V versus T, A versus T. Okay. Now, can you whip off those graphs real fast? X versus T, V versus T, A versus T. We're dropping a ball off the cliff. Let's say the top of the cliff is 0.0. Let's say down is positive. Okay, can you guys do that? Okay. By the way, be ready for to field it both ways. AP could change that on you. AP could make the valley 0.0 and they can make the top of the cliff like some elevation. I'm just sticking to real basic. Top of the cliff is 0.0. As you go down, you're going into positive territory. Okay. And these graphs follow the equations that I was just showing you. Those three kinematic equations. They all go hand in hand. All right. Guys, what kind of graph did you make for X versus T? Careful. Parabola. Right. Guys, exponential, EXP exponential, that's like 2 to the power of X. Parabola is like X to the power of 2. Guys, those are totally different curves, okay? Right, this is a parabola. Right? You hardly ever see exponentials in this class, but you see parabolas all over the place, right? Guys, what does V versus T look like? Linear. Yeah, with the slope of, the gravity field, right? Sometimes acceleration, we're general. And then what's the area under V versus T? Yeah, how far does it fall? Displacement, how far does it fall? Right? A versus T, what do you guys draw? Yeah, constant or zero. Yeah, well, sorry, constant value. We're ignoring air drag. All right. You guys got that? Okay. How about here, get a good look at this one while I'm switching this out here. I don't know. I don't know why it's just like doing this ticking thing, but I'm gonna try a little experiment here, see if this does any better. Oi. Is that not working at all, huh? Wow, that's even worse. Okay, you know what? Ditch that. All right, so could you guys feel throwing the ball upward, throwing the ball downward? Wait, you see how this is a little bit different from before? All right, gonna move on here. All right, let's blow up. You guys see this graph right here? I'm gonna blow this up real big. So let's say you go to the edge of a cliff, you throw a ball straight down, and then it only goes faster because gravity's pulling it down. So the speed picks up at a constant rate. That constant rate is, in general, acceleration. Could be gravity field, right? And then the area under the curve is how far is it falling. And guys, this rectangle is V naught T. This triangle, do a little algebra shuffle, is 1/2 AT squared. Put it all together. Hey, there's the first kinematic formula. X equals V naught T plus 1/2 AT squared. Right, you guys remember that, right? All right. Reaction time. You guys remember doing this one? You drop the roller, the frame catches it, and then depending on how far the roller is falling, you can calculate your reaction time. Okay? So, like as I'm speaking and as your brain is processing what I'm speaking, there is a little bit of a delay. Do you guys remember how much the delay is? Okay, yeah, can you guys derive that from scratch? Here, guys, write down the first kinematic formula. Here, I'll give you guys a simplified version. X equals 1/2 AT squared. That's if it starts from rest, right? Because you're not throwing the roller down there. Slow. Here, you're just dropping it. Okay, so can you guys write down X equals 1/2 AT squared? And then solve for T. Can you guys do that? I think your reaction time was, it was about 0.2 seconds. That's about a fifth of a second. So between me speaking and your brain processing it, yeah, there's a gap of about a fifth of a second. If you're driving your car and then like a deer runs out in front of you, it takes your brain a whole fifth of a second for your brain to process that and even begin to say, like, oh man, I should be slamming on the brake. All right, did you guys solve this? All right, here you go. Here's the first line. Well, because H is 1/2 GT squared. That's the same thing as X is 1/2 AT squared, right? H is 1/2 GT squared. Did you guys solve for T? All right, did you guys get that right there? All right. All right, now we're about to incorporate that into projectiles. Okay, there's your reaction time. Okay. See what's next here. Okay, yeah, of course you guys did the lab version. So hold on to that idea. All right, guys, car brakes to a stop. X versus T, V versus T, A versus T. Go ahead, draw those three graphs from car brakes to a stop. By the way, those graphs are drawn. There is one category of kinematic question. I don't know if you guys remember those that I can ask you that it's actually easier to solve with a graph than it is with the equations. It's one of the graphs you're making right now. So if I tell you a car brakes to a stop, so you know final velocity is 0. If I tell you, what else do I have to tell you? The distance the car brakes to a stop and how much time it takes. If I tell you those three variables, the distance, the time, and the final velocity. Okay. Then, yeah, you could solve it with equations, but it'd be a system of equations. It'd take a lot of paper, but you could solve it with a graph real fast. Okay. You guys got the three graphs? You guys got three graphs? Right. What'd you guys, here, let's go from bottom to top. What did you guys draw for acceleration versus time? Negative constant, because in this class, we're assuming uniform motion, so it can be constant. It's going to be negative because the car's slowing down. Right. What do you guys draw for V versus T?
Like down.
That's right. Starts with initial velocity, goes to 0, and of course, uniform motion in this class. It's going to look like a triangle type shape, right? Okay. What do you guys draw for X versus T? Ah, yeah, parabola with a vertex way out here at the top. Ah, like an upside down parabola, right? Because if you break this into time intervals, say the first second, say it takes 3 seconds to slow to a stop. The first second, the car moves a long way. The next second, not as far. And that last second, it's just rolling a little bit, coming to a stop. Slowing down, right? Slowing down, slowing down. It's going slower and slower as it's coming to a stop. Okay. Hey guys, that middle graph right there, if you dash off that middle graph for that question I asked a minute ago, if I give you how far, which is the area of the triangle, how much time, which is that t, and the final velocity, which is this final coordinate down here. Okay. It's easier to solve that type of question with that graph than it is with the equations. That's kind of a special scenario. All right, guys got that? Oh yeah.
What's the equation for xt?
What's the equation for what?
The distance over time graph.
For this right here? Okay, so it's just x equals v naught t plus 1/2 a t squared, right? Okay, right, and then where this v naught goes, it's however fast the car was traveling. Say you're going like so many meters per second, right? And you guys see this dashed line right here? Like that's the slope of this x versus t curve. That is the initial velocity. You guys see that right there? Right, so that goes right there. Right. However much time it takes to come to a stop shows up here and here. That could be this time right here. Right. This acceleration is, well, I guess this value or this slope, or it's kind of how curvy is that graph right there. And it's going to be a negative value, isn't it? Negative, right? Yeah. All right, guys, good. All right. What next? All right, there's a lot of info packed on this one. Okay, so your velocity could be positive or negative. That's moving forwards or moving backwards. Your acceleration could be positive or negative. That's like if you run the clock enough time, you're tending towards forward or tending towards backwards. Okay. Now, in combination with each other, here's moving forward, speeding up, moving forward, slowing down, moving backwards, slowing down, moving backwards, speeding up. Okay. And here's the xv and a versus t curves for each one of those. So, okay. Any of those could be questions, right? Yeah. Now that's a linear motion question, so I don't think you'll get that on Wednesday, but just in general. All right, now we're kind of properly moving into projectiles, but I wanted to recap everything that so far because it leads into it. Okay. Guys, remember this? I think this is actually how I began the projectiles. Is I started with suppose you blast 50 meters per second at 37 degrees from the horizontal. Okay, can you break that into components? Hey, that's where you break out the sine and the cosine. That's what we did. That was the first thing we did today, right? Because sine and cosine. Okay, so you break out sine and cosine. Okay, it's going 40 meters per second across the field and 30 meters per second strictly up as it's leaving the cannon. Okay, all right, guys, that horizontal 40 meters per second, does that say the same all the way across? Yeah, it's the same all the way across. Right, it never speeds up or slows down horizontally, right? Because there's no horizontal force. Right? We're ignoring air drag, and gravity only pulls vertically. Now, speaking of gravity pulling vertically, guys, how much is the vertical component of velocity going to change every second? By 10 meters per second. So 30 to 20 to 10 to 0. So slowing down on the way up, and it's speeding up on the way down, because that's what Earth gravity pulls. Of course, you guys know the more precise values, 9.8, usually round to 10. Okay. AP allows you to round to 10 also. All right, you guys got that? All right, put it all together. All right. Okay, so there's the first step. Right? There's the first step. So many of these. projectile puzzles, right? Right. I'll usually give you V blast and theta, and then you say, okay, well, I can find those two components, and then I can solve it from there. All right. Here's cannon fires from the edge of a cliff. Guys, what shape is that right there? Parabola. It's a parabola, right? You guys see, if you're up in a blimp watching this go across, it looks like it's going across at pretty much constant speed, right? But vertically, hey, look at that. It's see, like if you dropped a ball at the same time as you blasted one horizontally, which one would hit the ground first? Same time. So they always have the same vertical component, right? Same height at the same time, right? So okay, so that's like accelerating vertically, right? Put it all together and get that parabola. Now, can you take that and solve for? You're gonna find a couple things here. Okay. Let's say blast distance from the edge of a cliff. Suppose you know how fast it can fire. I know how fast the cannon can fire. I'll aim it straight and horizontal. How far does it go? So here, I'll kind of show this one to you guys. I need to consider two starting places, right? There's vertical and there's horizontal. What's going on vertically? What's going on horizontally? Okay. Now vertically, I left off the V naught T part because it's not, guys, leaving the cannon, it's not traveling up or down. That's why I left off the V naught T. See, like if it was blasted at some angle, I'd have to include that. Okay. But this is a simplified version. This is just the, like, as if you dropped a ball, have the same vertical motion. Right? Horizontally, how far it goes across this horizontal distance is, well, how fast it's going across times time. And how fast going across is the blast speed if you aim it horizontal. Isn't that true? Right? So here's your system of equations right here. Boom, boom. Two equations, system of equations. Right? And if you want to figure out something like how far does the ball go, you guys see we're going to have to substitute out the time. Right? So what I'll do is I'm going to take this vertical. I'll solve for the time. How much time does it take to fall? How far? I'm going to substitute that over here. Okay. And how much time it's been falling for? Hey, that's something you guys just derived a minute ago. Isn't that the reaction time right there? That's reaction time. Right, that's why we had to recap the linear to get the projectiles, because it's incorporated. Right, then can I just substitute that right there? Right, so V blast times that square root. Right. And then there you go. There's the blast. Well, there's the landing distance. Okay. Now, when you guys did this lab, you actually solved for something a little bit different, and that's the next poster here. You guys solved for blast speed based on where did the ball land, right? So you measured how high is this balcony. You blasted some balls. You went there, measured with either a trundle wheel or a meter stick. Said, okay, land so many meters out, right? And then you could back calculate what was the blast speed. Now it's the same initial setup. Guys, does that look like the same system of equations? I think it does in variable form. It's the same equations as the last, nothing different so far, except what we're solving for is different. Now we're solving for this blast speed, and you know this blast distance. Can you guys do that? Right? Because it's nearly identical, except it just changes right at the very end. Right? Just turn this around, solve for V blast. That's D over T, because horizontally it doesn't speed up or slow down. Horizontally it doesn't accelerate. Okay. Substitute, right? And it looks like that. Okay? That was exactly a lab that you guys did. You guys ever doing this lab? Right? You guys probably have this filed away somewhere. Okay. Yeah, that could be a really good FRQ. Right? I wouldn't be surprised at all if AP throws you that FRQ in May. It's like, solve for blast speed, and they give you everything you need. All right. I think your lab table looks something kind of like that, or I don't know. Maybe I had to go draw a lab table, one or the other. All right. Okay, that one would be kind of fun, but fun. All right. This one's a little involved. I don't know. All right. Guess ready to move on to, oh yeah, go ahead. Okay. All right. The next unit, forces and Newton's laws. So by AP's book, we're going from unit 1 to unit 2. Now, AP just this year, they shoved a ton of stuff in unit 2. We're going to ignore all the rotational stuff, all the gravitation stuff, all the orbits. So we're just going to bypass that for now. Okay. So just your orange banners, really. All right. So now we got some new variables that are going to matter. Okay, so we got mass. Notice all that kinematic stuff. The mass ended up not mattering or canceling out. What are they? Right. If you put a force on something, it's going to cause a mass to accelerate. Right? Mg is that mass times gravity field. Right, which is how I represent the weight of something. You also see F sub G. See F sub G, force due to gravity. It's the same thing. I learned it this way, so I just teach it this way. Right. What's the force from a surface? Normal force, guys. What's a synonym in math for normal? Perpendicular. Right. So this anything you put on a surface, the support force is always perpendicular to that surface. Right? So if it's an incline, right, it's going to go at some angle. Right? Coefficient of friction. The two types of coefficient of friction. There's you have a no speed between the two surfaces, or if you have one surface sliding past the other surface. And those are the two types there: static and kinetic. Okay. You could have a tension force. You could have how stiff is a spring, called spring constant, measured in Newton per meter. Okay, here's the units for all these over here. Right? Okay. All right. All right, well, guys, what is force measured in? Newtons. Yeah, newtons, right, which is kilogram meter per second squared, right? As in F equals ma. Does that look a lot like Newton's second law of motion? F newtons equals m kilograms a meters per second squared. That's what I do. So here, if I have here's 1 kilogram right here. Boom, 1 kilogram. If I push on this with 1 Newton of force, it's going to accelerate at 1 meter per second squared. Right? Is that it? Okay. If there's 1 Newton net force, I should say. Pressure, guys. What is pressure? You guys ever pump up your bike tires? Oh yeah, pascals is a good unit. Hey, what is 1 Pascal? 1 Newton per square meter. 1 Newton per square meter. Right now, what's the American unit for pressure? PSI. Is that like pounds per square inch? Guys, it's the exact same idea, right? So pounds per square inch. Hey, that sounds like a force per unit area because pounds is like a force, square inches is like an area. Well, the metric version is Newton per square meter, and that's pascals. Hey, does anybody remember we're in some atmospheric pressure right now? How many pascals of atmospheric pressure are we in? About 101,000. 101,000 of these, right? Oh, you can. There could be. Here, it could be pressure. Right. So, yeah. Okay. So, guys, a good question based on like this. Guys, here's a 100-gram lab mass. Guys, how many newtons does this weigh? 1. This is 1 Newton. It takes 1 Newton to lift this. I feel 1 Newton. It's like 0.98 newtons. I'll call it 1 Newton. Okay. Suppose I have a big old foam board. That's let's say about 3 by 3 floor tiles. That's about 9 floor tiles. Is that pretty close to a square meter? I set this on that foam board. I got 1 Newton on 1 square meter. How many pascals is that? 1. That's 1 Newton per 1 square meter. That's 1 Pascal. If you multiply that by 100,000, well, that's what all of us are feeling on our eardrums right now. Okay. Next one. Ooh, laws of motion. You guys ready to do Newton's laws of motion? What's Newton's first law of motion say?
Anything that is in motion will stay in motion unless
Aha.
acted on by enough outside force.
Boom! Nailed it. So object at rest will remain at rest. Object in motion will maintain its velocity. Now velocity is 2 parts to it. It's speed, but also direction motion. So things want to travel in straight lines, right? Nothing ever wants to speed up, slow down, or go around a curve. And if something ever is speeding up, slowing down, or going around a curve, then there must be an external net force acting on it. Okay, that's also called law of inertia. You guys remember that? Okay, guys, what does Newton's second law of motion say? Aha, I think it was an A. That's a good one right there. Okay. So net force is mass times acceleration. A lot of times I write this fraction form, like cause effect. If you put a net force on a mass, it results in an acceleration. Okay. That could be a linear acceleration, speeding up, slow down. But then later on, we said that could also describe going around a curve. This could be a centripetal acceleration. Could be. Right. And then, what's the third law of motion?
Equal and opposite between 2 objects.
Aha, yeah, the equal and opposite forces rule. There you go, right? So you have to have 2 interacting objects, and you have to consider each object. And if they're pushing or pulling on each other, here's a cannonball and a cannon. Here's like a moon and a planet. Right? Yeah, those forces between them are always equal and opposite. Right? Now, if I have you draw a free body diagram, or if AP has you draw a free body diagram, you're normally just focused on a single object. So normally don't draw the force pairs, right? But if you have 2 interacting objects, like boom, 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 okay, equal and opposite forces. Okay. So guys, when this cannon blasts this cannonball, is there a force on the cannonball? Yeah. Is there also a force back on the cannon that forces the cannon backward? Okay, but which force is bigger? The same force. Does the Earth pull on the moon? Yeah, it keeps it in orbit. Does the moon pull on the Earth? Yeah, that's why you have tides, right? Okay, but which force is bigger? They're the same. Get tricky guys. Tricky someday, tricky Griffin. Okay. Different perspective on third law. Okay. All right. So here's a second law type. You can bridge kinematic motion to this dynamic motion, right? With acceleration, this is bridge variable, think like this. Okay? So back in kinematic days, we were looking at things like speeding up and slowing down. They're like, okay, what's the acceleration due to speeding up and slowing down? Now we're getting to what causes that acceleration. It's a net force acting on a mass. Okay? Then you can go back and forth. So if you look at the motion and say what force resulted, you go from left to right. Or we've done plenty where you go the other way, where I say, well, like, if there's a soccer ball and you kick the soccer ball with some force, like how fast is it going to be going? So you say, okay, well, like some force on some ball, some math, you can get the acceleration, how fast it's going, maybe one of these over here. Okay. When we eventually get to rotational, we're gonna have to save this for January, right? You guys remember I talked a little bit about torque last week, a little bit about torque, right? So that's kind of like a force, but in a rotational sense. So if you put a torque on that turntable, you guys remember those turntables? That would cause it to speed up spinning. That's called angular acceleration. Right. It's a little sneak preview to January. Okay. All right. Ooh, guys, Hooke's law. You guys remember spring stretching and could compress, could stretch depending on what kind of spring you have. Right. Guys, what's a formula for Hooke's law? Boom. F equals kx. Right. Right. Now, more recently, when we started learning about energy, I pulled this poster back out from long ago. And I say, hey, there's another property that we didn't look at so much, which is the area under this curve. Guys, what does the area under that curve represent? The what? Yeah, the energy stored in the spring, right? Which, is, by the way, is also how much work it took to try to compress the spring in the first place, right? That green triangle right there. And that's your 1/2 kx squared. That's from really recently, from the past couple of weeks. How much energy it takes to stretch and compress the spring, therefore will be stored in this spring, okay? Conservation of energy, okay? Guys, having taught this class so many years, a lot of students mix up these two formulas. F equals kx, energy is 1/2 kx squared. Right? You guys know different contexts for different units, different concepts, right? Right? How much force, which changes, how much energy. Okay, get that. All right. All right, free body diagrams. We're going to label all forces acting on an object. So sometimes you see these called force diagrams, right? A moment could be a torque. Right, so when we eventually get to torques, we'll bring in those also, but that's like the rotational version of a force. Sort of, right? Guys, are velocity vectors on your free body diagrams? No, right? If I draw a velocity vector at all, I usually draw it off to the side as a fat arrow to clearly distinguish it from the force vectors, right? And just to provide context, because sometimes there's like a friction force that resists that.
If you do draw a velocity vector on your AP exam, but you like put it off to the side, do they count it?
Okay, guys, if AP wants you to draw a free body diagram, I think the safest thing to do would be to not draw the velocity at all, right? You draw one, maybe draw it in lemon ink. You guys gonna bring your bottle of lemon ink, or like draw a little fat arrow and then erase it. Okay, yeah, right, guys have that. All right. Right. Ooh, guys, rocket in deep space at constant velocity. Can you guys draw a free body diagram for that? Oh, everybody did it. All right, there are no forces. Great. Oh man, you guys remember that one? Guys, constant velocity. What's the net force for anything constant velocity?
0.
Yeah, there's zero net force. And in fact, if you're out in deep space, there's probably no gravity nearby. If you blasted these engines, the rocket would speed up. That would be acceleration, which would not be this. Yeah, there's no forces. It's just going. Isn't that kind of like a Voyager 1 spacecraft? Okay, that's actually my first law picture right here, guys. Here's Voyager spacecraft here on Newton's first law. You guys remember this? Right, it's just going. It's been going since the 1970s. It doesn't need any fuel. It's just going. All right, let's do air hockey puck at constant velocity. Air hockey puck. Okay, so it's on a flat horizontal table. Guys, air hockey, is there any friction? Nope. Right? It's just going across the table at constant velocity. Can you guys draw the free body diagram? All right, you guys got it? All right, what force did you guys draw? Aha, yeah, it's got the weight down and the air jets holding it up. If you write normal force, I'll take that too, but really it's the air jets, right? Okay. All right. Guys, is there any sideways force on this? No. If AP wants you to draw this, you're just gonna really just draw that, right? Okay. I put this here for context, but it's not. This V is not part of the free body diagram. All right. How about let's say we're on a tabletop that has some friction. I'm gonna drag this across. Can you guys draw the free body diagram for that? What forces did you guys just draw? Okay, yeah, there's all four right there. Boom. You guys just said there's right. This block has a weight pulling down. There's the normal force from the surface holding it up. Normal is perpendicular. Yep, straight up would be perpendicular to surface. All good. Okay. Okay, so say pull it horizontally, so that has to be this applied force here. Okay. And then constant velocity. Guys, what do you know about the net force again for constant velocity? 0. So if you're pulling and it's also moving constant velocity, the only way for that to happen is there's got to be this resistive force here that I'm calling friction. Right? If there wasn't, then it wouldn't be constant velocity or you wouldn't be pulling it, one or the other. Okay. So do you guys see all the forces zero out? They zero out vertically, they zero out horizontally. Okay. You guys look at this force, friction force, versus this force, normal force. What's the ratio of these two called? Coefficient of friction. At least that's true for kinetic friction. That's true, right? Static friction, you can build up to that point. That's why there's this inequality. Okay. You pull a little harder, a little harder, a little harder. Right. Also want to say, okay. Also, of course, you guys know friction force is equal to supplied force and normal force is equal to the weight. So in the lab version, I had you guys just take the ratio of these two, but it's not the same thing. All right. Now, guys, coefficient of friction, is that a material property? So once you know what the materials are, it's established what it is, right? Like these last 3 rows here, I have driving cars. Haven't we done like so many cars break into a stop? And if you gave me a coefficient of friction of like 0.1, I said, oh, it's probably iced over. It gave me a coefficient of friction of like 0.9. So, oh, you probably have new tires and road's dry. Right, here's the road is wet. Right, kinetic, static, like that. Okay. You commonly see like 0.2, 0.3, 0.4, 0.5. Those are common coefficients of friction. Okay. All right. All right. I think you guys hit this lab. Ooh. Okay, you guys ready for a challenge question? Challenge question. Car brakes to a stop. Here, I'll give you guys the first line. Is Newton's second law of motion. F equals ma. I want you guys to solve for what's the acceleration of the car. Which I guess could be a negative value. I forget if I put the negative sign on this poster or not, but car's slowing down. Okay. Or what's the magnitude of the acceleration? What rate is it slowing down? Out in the wild, you might say, what's the deceleration of the car because it's slowing down? Okay. Guys, I'll give you guys a little hint while you guys are driving this on your paper. Coefficient of friction is somewhere in there. So in the answer, coefficient of friction is somewhere in there. Let me throw another hint at you guys. Do you think the mass of the car ends up canceling out somewhere before the end? How about do you think the gravity field of the planet matters? Like if you're on Mars versus Earth, do you think the car could slow down at different rates?
Yeah.
Okay. Say coefficient of friction, something to do between the tires and the road, the rate the car can slow down. Okay. All right. Let's solve this thing. Guys, what'd you put for the net force of the car? Friction force, friction force. Yep, there it is. The friction force is the net force because the two verticals cancel. Right? You guys, friction force is equal to what times what? Coefficient of friction times the normal force. Okay. And so that's that, right? Oh, and the normal force is equal to what? mg. Right? Is that it? Hey, what cancels at this point? The mass of the car. So there's the rate the car can slow down. If I went back and tidied this poster up, I might slap a negative sign in there somehow, but that's the rate the car can slow down. Right? Coefficient of friction times gravity field. So for example, if the coefficient, suppose it rained earlier today, and its coefficient of friction is like 0.7, and Earth's gravity field is like 10 meters per second squared. Could you slow down at about 0.7 times 10? Is that like 7 meters per second squared? That's as much as you could ever slow down. Plane constant velocity. Plane constant velocity. Yeah, I remember this being a military entrance question, and yeah, some of my students confirmed that. Dude, right? They'll say, what are the four forces on a plane? And you guys say, what, and what?
Wait, drag.
Whoa. All right. Man, that sounds like you're talking to a drill instructor. Yeah, we got weight, lift, thrust, drag. Boom. Right? You guys, concept velocity. What do you know about the net force? 0. You guys, do all those forces cancel? Yep. I think the weight and the lift are canceling. I think this thrust and this drag are canceling. Yep. All right. Now these next few here, I might go through a little bit fast, maybe. All right. Now let's consider air drag. This is the first time we started talking about air drag because normally we ignore that in this class. Okay. Now here's true free fall. Guys, true free fall, there's only one force, which is what? The weight. But if you consider air drag, isn't it true the faster you fall, the more the air drag builds up? But guys, that air drag can only build up to how big?
Velocity.
Right. It can only build up to as big as the weight, at which point it's reached the terminal velocity, because now it's not accelerating anymore. Does that mean it just bing, stops midair? Is that what that means? No, it means it moves how? Constant velocity. Oh, wait, to ground. It's terminal velocity, isn't it? Right. Here's the full equation. I don't think I'm really going to ask guys about that. Here's just a little bit bonus, right? I saw this in college a few times. Take engineering in college, you might see that a few times. All the factors that go into like drag force. Okay. V versus T. Here's a good question. So it starts off at V versus T as if it was in free fall. It will slope equal to gravity field. Right? But hey, it's gonna eventually taper off to terminal velocity, like a horizontal asymptote. Right? The one time I ever saw this equation solved, it was in a post-Calc 3 class called differential equations, and well, I survived that class enough to make this poster. So that's a really tricky equation right there. Don't ask me to make it quick. All right, block on an incline. You know what? I think bell's about to ring. So we're gonna have to pick up tomorrow with block on an incline. Because this one you definitely need to know. Okay. So tomorrow we'll continue the review. We'll do one more day review. We're gonna start with the block on the incline. All right, skip pause point today.